Unit 2 essay question number 4. So in your eye, you can focus light using the lens of your eye, which I've drawn there in blue. So we see light in our eyes through. There's a focal point that we see, and then it reaches our eye, and it bends through, and we bend light to receive it in the back of our eye at the retina. When light bends, light bends differently whether or not it's close or far away. The rule of thumb is that the closer the object, you bend light more. And this is achieved by changing the lens. When we have that suspensory ligament attached to the ciliary body muscle, let me just draw a version of that over here. It's kind of like a little inner circle with some suspensory ligaments that come off of it, with another little muscle that comes around. So as this muscle is moving in and contracting, the ligament is becoming looser, which makes the lens fat. It kind of opens the lens up to more of this kind of oval shape, as it's contracting. But as it starts to move out, we have a lens that looks more like this, and so this is during its relaxed stage, and this is when things are they're further away. So this is for a far, and this is for a close object. So during this closer object, we will bend the light more through this lens. It comes from further in and bends more severely. And so we can see things that are up close and things that are far away. And as you have issues with your eyes, you get lenses that are either concave or convex or both, and that will help you bend light so that it reaches the back of your retina here at one point. If it reaches this point and this point, then it will look blurry to your brain. You perceive that as blurriness, and you can no longer see it effectively. Now we're going to talk about how the photoreceptor cells, which are rods and cones, end up giving us our sense of light. So there are two photoreceptive cells, which are these black lines here, and they're made up of rods and of cones. So a rod is how we see black and white, and the cones are how we see color. We only perceive red, green, and blue colors, and our brain can interpret amounts and concentrations of those into many, many different colors. In the eye, once we get past, the lens was here in the previous section, and then there's some blood vessels behind that, but light is coming in and hitting these photoreceptors, and the photoreceptors send signals through to the bipolar region and then to the ganglia, and then the ganglia cells converge together onto the optic disc and into the optic nerve, and then off to the brain. So we'll talk about these three and how we perceive light. So this is them kind of blown up. We have this photoreceptor cell here first. So if light were to come in and hit this cell, how would we draw that on there? We have have light come in and hit this. That's light. This we call 11-cis retinol will go through a conformational change into 11-trans retinol. That 11-trans retinol will activate this alpha subunit. And it will move to activate PDE, which is phosphodiesterase. So that turns on. When phosphodiesterase turns on, it will affect this cyclic GMP channel here. It will start to break down cyclic GMP into just GMP, which will end up closing this sodium channel and not let that sodium through. That sodium is needed to keep this calcium channel open and working. When this calcium channel no longer is being activated, these vesicles will no longer be, or at a much less rate, will be moving glutamate into the synaptic cleft here. So then we move to the bipolar cell. So the bipolar cell, because there's not much glutamate here, will not readily activate mGluR6, which is one type of receptor. There is another receptor here called AMPA, and AMPA is excitatory and mGluR6 is inhibitory. So the small amounts of glutamate that are coming through will start to inhibit, because it will only be able to activate this mGluR6. So it will inhibit the tropin-1 calcium channels, which are these. So it'll do the same thing as before, like I talked about here, where the vesicles will not be able to move the neurotransmitter glutamate out into this synaptic cleft area, which, again, because not much glutamate, we cannot affect AMPA in the ganglia cell, and so the action potential that is sent is saying that there is light, because there is no glutamate activating this area here. So our rule of thumb is that when we have darkness or a lack of light, there is more glutamate from the photoreceptor, and when there is light, less glutamate is being released from the photoreceptor, which is the photoreceptic cascade that sends through this and into the optic nerve for us to be able to see. And that's how we perceive light. The final thing that I want to talk about is how this is the bipolar cell and how it is affected by the center and surround molecules that are found just adjacent to them. So when glutamate here is slowed down because of a lack of light, because of light, glutamate is slowed down. AMPA here is not activated. Because of that, we have GABA release here, which is an inhibitory molecule, and when we try to bind here, the mGluR6 is what's activated because of a lack of glutamate flowing through this cleft, which is what tells us there is light. But that was only the case if this is the on center. It needs to be turned on. And we always know that the surrounds do the opposite of the center. So if this is an on center, then these are off surround. And that off surround will go through as I described and slow down if light hits all of this. And the surround is off, then glutamate will be not being released, which no AMPA activation, which means inhibitory GABA, which means not much glutamate here, which means mGluR6, which shows as light to our brain. If it were the opposite cases of this being on and this being off, then the glutamate would release, activating the AMPA, which GABA would not be inhibitory because it wouldn't be released, and you would have a glutamate flood AMPA on the bipolar cell, which would tell us that it is dark. And this is a molecular level of inside of the bipolar cells and how they work. And because of this, we're able to interpret darkness and light.